Hello and welcome to this introductory video about capacitors. In this video we're going to introduce what capacitors are and a little bit about some of their properties in order to understand a little bit more about them. So what capacitors are is essentially they are just big charge reservoirs. So they store some charge. As a result of that, we'll see that they basically end up storing up some potential, which means that we can use them then to make interesting things happen in circuits. They have quite a lot of applications, but we're going to keep things simple for now. So we're going to introduce the most common sort of capacitor that people like to talk about, which is the so-called parallel plate capacitor. And by that we just mean we take one conducting plate of metal and we take a second one and we just put them so that they're parallel to each other. And then what we're going to imagine is that we basically put, say, minus Q on that one and a charge of plus Q on that one. Okay, in terms of the charge distribution, we know that that's going to be with them on the edge of this conducting plate, kind of uniformly spread because they're all balancing the forces and so on. Alright, so they're just nicely balancing the forces on either charge because of the electrostatic equilibrium condition. So this is sort of what we've got imagined. Of course, in the real world, you would maybe connect this to some circuit that connects off to a battery, which is how you put some charges on here. But it doesn't really matter. For our purposes, we've just got the charges sitting on the plates like this. So let's think about what that means. But before we continue, we should also note a little bit of an ideal case here going on. So I haven't worried about what's going on at the edges, which would be quite complicated and a bit difficult to figure out exactly how many charges you need to squash there to then balance the rest of them. So why haven't I bothered? And that's because whenever we talk about parallel plate capacitors, we have in mind a so-called ideal case. And the ideal case is that the plates themselves are actually infinite. Okay, now that sounds pretty ridiculous. Nobody could actually go and build infinite plates, so why would we ever care about infinite plates? Well, it's because we don't actually mean infinite. They don't have to be infinitely large. What we really mean is that I can draw something that kind of looks like this and not worry too much about what goes on up here or down here. And the condition for me to not worry too much about the edges is basically what I want is if these plates have some separation D and some big overall area A, so the area of A, then I want that area to be large compared to the separation. Or really I want the length of one side to be large compared to the separation. Okay, so that's what we mean by infinite. And you just are never asking about right here, because no matter how big I make them, if I'm right there, I still have to worry about the edges. So we're talking about looking kind of in the center for a small separation compared to a rather large side length and hence a rather large area for our parallel plate capacitors. A nice conceptual way of thinking about this is simply if you imagine that you are sort of a fly or something and you're flying around in between here. If the separation is small, then you can't get very far. You can get maybe over to here. So let's say we fly over to here. And then we're looking at this thing, so maybe this is our field of view. I don't know what the field of view of a fly is, but let's say it's something like this. Since that field of view sees nothing but the opposite plate, that is a good parallel plate capacitor. Because I'm sitting at this point, all I see is a bunch of plate. I can't tell that it's not infinite. On the other hand, if this plate was very much separated and I had my fly out here, and I tried to draw in this sort of same field of view, right, this fly can see that that far plate, and in fact even the near plate, do not go off to infinity. It sees all of this, and all of this, and this, and this as not being a plate. So this fly is well and truly aware that these things aren't infinite. So that would mean if I had another plate that was here, then this large separation, we'll call it capital D, that's too big, and this thing is not. So this plate plus this plate would not be ideal. This one plus this one are pretty ideal. Okay. All right, so we just mean this idea. We're not looking for largely or widely separated plates. So this infinite thing means we're not looking at widely separated plates. We want small separation compared to the area. All right, so let's talk about some of the properties of these plates. So of course, I mentioned that by storing a bunch of charge, we're going to create a big potential difference across these plates. So let's talk about that and go back to our nice original plate that was working as a good ideal parallel plate capacitor. So if we're doing this sort of thing, then let's talk about the potential. So here we are, beautiful parallel plate capacitor. It's pretty ideal for most of the points inside. Of course, we'd like to know what is the potential from one side to the other, so we'll call that the potential, maybe V from A to B. What's that going to be? Well, we can write it like this. It is minus VB minus VA. So it's minus the potential at B, minus the potential at A. Okay, the negative of that quantity. And the reason we're doing it this way is because this thing nicely turns into minus the potential energy as you move from A to B divided by Q. And the potential energy is the minus of the work. So that is the work divided by Q. Okay? Because there was this overall minus sign between the potential energy and work, we've gotten rid of our original minus sign. So now we're just looking at VAB is the work divided by Q. What is the work? Well, let's take a look here. We've got this nice parallel plate capacitor. We said it's ideal. So why do we care that it's ideal? Well, because then we could talk about the charges being nicely spaced like this. And we could introduce then thinking about what the field is doing. It points away from the positive over to the negative. We've drawn them slightly out of line with each other, but there we go. So we get a nice uniform field going across this thing. If the field, right, all the arrows are parallel, that's talking about the field strength, it's not changing. The direction is always to the right. So we have a nice uniform constant field throughout. So then we can write that the work is just the force times the distance divided by Q. But we know what the force is. It's the test charge times the electric field, which is nice and uniform. Those are the vectors we just drew in there. So it's just QE times D on Q, and D is just as we moved across the plates. Okay, so the potential in this nice parallel plate capacitor is just E times D. All right. So that is a very important property of parallel plate capacitors. Now another thing that we like to talk about is capacitance. And capacitance is telling us something about how much charge we can actually store. And of course that's important because the electric field is going to be proportional to the charge. Okay? Right, the more charge I have, the more lines I would have drawn, the denser it would have been, so the stronger the field. So clearly the electric field is proportional to charge, and the potential is proportional to the electric field. So we know that the potential is proportional to the charge on the plates. So if we just write this thing that V is proportional to charge, two things being proportional just means that we can write something like maybe that Q is some constant C times V, or dividing through by the V, we can solve that C is just Q divided by V. And that is exactly what we do. We write down a capacitance for the capacitor, which is just Q divided by V. So basically it's telling us what is the amount of charge I need to get a specific potential difference across this thing. Okay, and so the more charge I can store, the larger my voltage would be, because the capacitance then is some constant. It's a property of this parallel plate capacitor. Okay. Now, let's look at the units. We've got a charge, which is a coulomb, divided by a voltage, which is in volts. So it's a coulomb per volt. We introduce a new name for this. We call it a farad. And typical things are in the milli to even picofarad range for capacitors. And then it is possible to go through here and show that for a parallel plate capacitor with area A and separation D, that what you get for the capacitance is just epsilon naught times A times D. And epsilon naught is something called the permittivity of free space. It is a constant which you can look up. Now, one other thing that we can do is, because I'm talking here about the capacitance of a parallel plate capacitor with the permittivity of free space, that means I'm talking about imagining actually that there's nothing between these plates. There's just a vacuum. But in reality, there could be air. Maybe I put some paper in there. I can put any kind of material there. And what that ends up doing then is just changing things slightly into this second form down here. So it ends up making things have an extra constant that scales up the capacitance. Okay? And that extra constant is what we call a dielectric constant, because we talk about putting things in between here as dielectrics. So those are insulating materials which result in a change in the capacitance of the parallel plate capacitor. You can look up a material's dielectric constant, and then that is what that kappa represents in that expression. Okay, so then some food for thought. We know that we can write down that the capacitance in general is some dielectric constant times epsilon naught A on D. So what must be the dielectric constant for vacuum? And sort of a more interesting thing to think about is, suppose that what I've got is a set of parallel plates and they're connected to a battery, so it's maintaining them at a fixed potential difference, and I insert some dielectric. So I change the dielectric constant, it becomes larger, so I increase C, the capacitance of my capacitor. What effect does that then have on the amount of charge that I'm actually storing in those plates?